Our first speaker from the last session today is Elizabeth Collins-Woodfin from University of Michigan. Take it away.
Hi, thank you very much to the organizers for this opportunity to speak. Today I'll be talking about overlaps of a spherical spin glass model with an external field. This is joint work with Jinho Baik, Pierre Doussal, and Hao Wu. And there are also similar results obtained in a separate paper by Ben Landon and Phil Soso, and I'll have references to both of those at the end of the talk. Oops. Sorry. There we go. So I'll start with a general introduction to the spherical Sherrington Kirkpatrick model, which is what I'll be focusing on today. And the key question is, how does an external field affect the distribution of spins? So in order to study this, we need a tool called overlaps, which I'll define, give a bit of information there. Then I'll present the results for the model with an external field, as well as the model without an external field. And then finally, I'll talk about the transition between the two models. So by way of an introduction, background on spin glass models. These models originated in the study of disordered magnetic alloys, but more recently they've found applications in many different areas, including optimization problems in computer science. I'll focus on the spherical Sherrington Kirkpatrick or SK model, and this involves a spin variable sigma, which is a vector that lives in an n-dimensional sphere with a radius of square root of n. And this is a continuous analog of the standard Sherrington Kirkpatrick model, which will also, I think, be mentioned in the subsequent talk today. But that one is discrete space, so the vectors have only plus or minus one entries. The SSK model is quite similar to the SK model, but in a lot of cases, it's easier to analyze due to its continuous nature. So the setup for this model, we have an interaction matrix M. This is an n by n matrix from the Gaussian orthogonal ensemble. That's been mentioned before, but if you're not familiar with GOE, the two key things to remember is that it's a symmetric matrix and that the entries are Gaussian and independent up to the symmetry constraint. We also have an external field, which is a Gaussian random vector of dimension n. And the strength of the external field is given by a non-negative scalar little h. We have this definition for the Hamiltonian. You'll notice that it has two terms. The first depends on the interaction matrix, and then the second depends on the external field. And so when we talk about an SSK model with no external field, we're just setting that second term to be 0. So then the spins in this model are distributed according to this Gibbs measure. And you'll notice that it has a parameter beta, we call that the inverse temperature, and that's a positive parameter. And then we divide by Zn, the partition function. And so that's just to normalize to make sure that this is in fact a probability measure. And one thing to think about when we look at this is that the spins are going to concentrate in regions of the sphere where the Hamiltonian is large. So we see this Hamiltonian in the exponent. When that's large, the probability is going to be large. All right, so we want to talk about the distribution of the spins in this model. And before I get into the technical details, I want to just kind of talk about it from an intuitive perspective. So this is the Gibbs measure definition that I presented on the previous slide. And today I'll focus on the low temperature case. So that's when beta is large. And we focus on this because it's sort of the more interesting case. This is where we see a concentration of the Gibbs measure in a particular region of the sphere. And we also see distinctly different behavior between the model without an external field and the model with an external field. So starting with the case of h equals 0, which is when there's no external field, the Hamiltonian is just that first term. And if we look at this here, that's going to be maximized when the spin sigma aligns with the eigenvector, which we'll call u1, that is associated with the largest eigenvalue of m. And so if the spin is close to plus or minus u1, that's where we expect the spins to concentrate. That's where we see the highest value for the Hamiltonian. In contrast, if we look at the case of h greater than 0, now we have an external field, and we have that second term which is going to be maximized when the spin aligns with the vector G, the external field. And so in that case, we'll expect the spins to concentrate near the external field. All right, so to get into some more precise analysis of that, we need overlaps. The first overlap that we'll look at is the overlap with the external field. And so this you can see is a normalized dot product of the external field with the spin vector. And so you can say, you think this is just the cosine of the angle between the spin and the external field. So this is just telling us how close is the spin to the external field. We also have an overlap with the ground state. So ground state is another name for that eigenvector I was talking about before, U1. And so here we're looking at the square of the cosine, the angle between the spin and the ground state. And we use the square here just so that we don't need to deal with the ambiguity in terms of the sign of the eigenvector. In the paper, we also look at one other type of overlap called the overlap with a replica, but due to time, I won't be discussing that today. Then one thing that I want to note before we go to the results is that because we're in a very high dimensional space, if we were to take vectors drawn uniformly at random from the n-dimensional sphere, we would expect them to be nearly orthogonal. So if sigma was drawn from a uniform distribution, we would expect that both of these overlaps are close to zero. And so on the next slide, when I start presenting results and you see cases where the overlap is away from zero, that's indicating some concentration of the spin in a particular region of the sphere. All right, so here are the initial results for these two cases. We look first at the overlap with an external field. When H is equal to zero, the overlap is very close to zero, as you would expect, right? There's no external field there, so that's going to be close to zero. But when H is greater than zero, we see that the overlap with the external field is given by this function, which is of order 1, and we can actually get an explicit, in our paper, there's an explicit expression for that function, but it's an increasing function of H. And what that tells us is that when H is greater than 0, the spins concentrate on a cone around the external field, and they get closer to the external field as the strength of the field increases. And that geometry of a cone, that comes from the fact that this overlap is measuring the cosine of the angle between these two vectors. So now let's look at the overlap with the ground state. Here we kind of see the opposite thing. So when H is greater than 0, this overlap is really close to 0. But when we see when H is equal to 0, so when there's no external field, the overlap with the ground state is roughly 1 minus t, and t is smaller than 1. So what we see in this case is that the spin is going to be concentrating around either plus or minus U1, the ground state, and it's going to get closer to the ground state as the temperature decreases. This was also studied in a separate paper by Penchenko and Talleyrand, and they find that actually the spins are uniformly distributed on that double cone. So I'm going to give you these two pictures here. Obviously, in an n-dimensional space, these are not really capturing the geometry, but hopefully it'll at least kind of give you a visual tool for thinking about the spins in the external field case where they're concentrating near the external field, and then in the case where there's no external field and they're concentrating near plus or minus of the ground state. All right, so a natural question to ask here is we see dramatically different geometry between these two cases. So what is happening in between? How is this transition occurring? And so these are the results from the previous slide. We're going to look at two transitional regimes. The first is when the strength of the external field scales like n to the minus 1/2. And then the second is where it scales like n to the minus 1/6. Okay. So for the case of n to the minus 1/2 scaling, if you compare those two columns, you see they look very, very similar. So the spin distribution is similar to the H equals 0 case. And in particular, if we look at that last column, the overlap with the ground state, that's showing us that the spins are still concentrating on that double cone around the ground state. But if we look at the overlap with the external field in that first row, we'll see that now, even though it's still very small, it has a positive mean rather than a mean 0. Sorry about the resolution there. And so that shows the spins are more likely to be on the side of the double cone that is near to the external field. They're getting slightly pulled toward the external field. And that's indicated by the fact that even though this overlap is very small, it now has a positive mean. So that cosine is more likely to be positive rather than negative. We now want to look at the case where h scales like n to the -1/6. And here's where we see a more dramatic change. So let's focus on the last row there, the overlap with the ground state. We have the 1 minus t as we did before, but now there's an additional term getting subtracted. We have an explicit formula for this, and it's actually random. It depends on the matrix and the external field vector. And so what this tells us is that we're still on that cone, right? So we're still concentrating somewhat near the ground state, but now the angle of the cone is getting wider because of this term that's subtracted. And then if we look at the first row, the overlap with the external field, now that is strictly positive. And so what that tells us is that the spins are almost surely on the side of the double cone that's near G. So if we think about this double cone that we had before, it's gotten wider, and it's also, the spins are only on one side of this. So depending on which side of this is closer to the external field vector, that will determine where the spins are most likely to be located. So that's the information that I wanted to present relating to these results. I want to just very briefly give you a little information about our techniques that we used. So the first ingredient is a contour integral representation of the partition function. So recall the Gibbs measure, it's got this Zn in the denominator, and a priori that is a surface integral on an n sphere. And it depends on all of the entries in the matrix. So that would be a very complicated thing to compute. But due to special properties of the SSK model, we can actually rewrite that as a contour integral in the complex plane. And it has a function that depends only on the eigenvalues. This is something that's much more feasible to compute. And to deal with that, we make a moment generating function for each of the overlaps, and then we use the steepest descent method for contour integrals. I'll make one more note here that a priori, the steepest descent method is for deterministic functions. It wouldn't necessarily apply to an integrand that's random, but due to eigenvalue rigidity and things that we know from random matrix theory, this actually does work. And so we use a variety of things, including the semicircle law, so CLT for linear statistics of eigenvalues, and rigidity of eigenvalues. So I'll stop there, but I can answer more questions about that if people are interested. And here are the references that I used for this talk. Thank you.